Okay. All right. Hello. Hello. Can you? You can't hear me. Uh-oh. All right. Let's. How about now? Still. Sit.
What? You've been wearing a mask for class until
Yeah.
I was like, something is different. I don't know what.
Was it better before? No.
You look great.
Oh, now you have to say that, right? Okay. Are we ready? Okay. Homework 5. Wednesday, 10 p.m. We have a midterm. On Friday, right here, 2:40, 65 minutes. Same pretty much as midterm 1. The questions will be different from midterm 1, though. It'll cover material up to and including probably last Wednesday. So I actually covered the factorial on Wednesday, but that won't be on it. Okay. Any questions before we get started?
Just about the class in general?
Sure, about
I'm
general.
assuming it's an after-class Q&A type thing. Ask technical questions about Lab 6.
You can ask about Lab 6 now. I have a lot of time today, I think. No? No Lab 6 questions?
I will wait until the end.
You'll wait till the end. Okay. All right. So there are no questions. I will start talking about asynchronous outputs and what not to do. Okay. All right. So this is kind of a cautionary tale about synchronization and cleaning up signals. All right, so this is are we ready?
Yes.
Yes. Okay, so this is a case study. This is a fictional design. There's no such thing as a sequential access memory, thank God. Okay, no one would buy it. All right, so the idea here is we want to build something called a dictionary. And this dictionary basically is going to be provided an 8-bit key and a start signal. And it will somehow inside this dictionary is a lot of data stored, and the first data found that matches the key is supposed to be returned on the output. Of course, this may take several cycles to find this data, so there's a ready output that says, oh yes, I'm done. I've looked for it, and either I've found it, in which case it's out here on the 12-bit bus data, or if ready is high and found is not high, that means that there's no data in there that matched the key. Okay, so that's what we want to build. Okay, to do this, we need some kind of storage device to hold the data, and we have decided to use something really cheap called a Rolodex, and it's really cheap because they can't sell any. It's a 20-bit sequential access memory. Okay, not a. And the way we're going to use this device is it has 20 bits, and we are going to dedicate the upper 8 bits to hold the key. And so basically we're going to search all 20-bit words looking for a word where the top 8 bits matches the key. And the first one we find, we will then return the lower 12 bits. Right? So the data is stored as key data. Okay. All right. So we now need to build a circuit which is going to search this Rolodex for us. Okay. I have to tell you a little bit about this Rolodex. So this is the device we bought that was really cheap to do this. And what's the first thing you notice about this device? Yes.
That the inputs are first and next.
Okay. And
Not a specific index.
not a specific index, right? What else do you notice about it? Yes?
It looks like a counter.
Does it? I mean, isn't it?
It has a reset in first. It has an increment in
Right,
next.
but what doesn't it have?
A UTC last.
It doesn't have a clock. Right? No clock. Oh. So first and next are asynchronous inputs. They can go high. Are you guys looking at the slides?
I'm not.
You're not. Clara's not. Okay.
I have my notes.
Okay. All right. All right. So first and next are asynchronous inputs. So they are active all the time. They can be active at any time. And the Rolodex might respond to them. But the Rolodex has certain expectations on how you're going to use first and next. There's probably a pulse width requirement, which we'll just assume we can meet. So we're not going to pay too much attention to that. But this is how you are intended to use these inputs. So if you wanted to go through the Rolodex, so this is sequential access, so you have to go through every single word in order. Much like searching a linked list. It's not the best way to find things, but never mind. So in order to use this device, you would first give it a high pulse on the first input. And after this high pulse, after the falling edge of this high pulse, suddenly the first word will be present on the output. And then you can give it a next pulse, and what that does is it advances it to the next word. And you can keep doing this. And then eventually, when you are at the very last word in here, the last output will go high, indicating it, that's all. Okay, so this is how this device works. All right, so you see the last pulse here. Apparently there were 1,928 words in here. Okay, and this is what the timing would look like if you were actually in XSIM. Let me see if I can make this. Can I make this bigger somehow? I can make it bigger on my screen, but I guess not. That did not work. Guess not. All right. So anyway, you can see the first pulse here. There's unknowns here. And then the first word comes out. Okay, now this is actually all 20 bits coming out, right? Because these are 20-bit word. And then the last word here was 87. And if you give it the first pulse here, then you'll reset it to word 0. Okay, so let's build this thing. All right, so we're building this dictionary that's going to search for a particular key, right? So the key is an input. We're going to have go as an input. We probably want to turn that into a pulse, so we'll put an edge detector there telling us, okay, start. Okay. Oh yes, the clock. So we are a synchronous system, right? So the dictionary that we're building is actually taking a clock, so it's going to be operating off a clock given by the system that it's in, probably. But it's using this Rolodex inside here, which is not synchronized. Okay. All right. What else do we need? We're going to need to know when we found the key. So for that, we're going to need an 8-bit comparator, which you know how to build. You know how to compare two buses and check whether they're the same value. Okay. And the other 12 bits, that's our data. So we'll just connect that to the output. So the idea is we're going to run the Rolodex up until we hit the key, and then stop there. And therefore, if we find the key, then whatever these 12 bits are the required data. Okay. All right. So our comparator is going to be used to control the Rolodex, right? We need to have a state machine, and this state machine needs to know when it should start search, because when is the key valid, and when do you want to search? It is responsible for generating the first and next pulses, which operate the Rolodex, reset it, and run it until the key matches. And it knows when the key matches because it's got this output from the comparator. There's one other thing it needs, which is the last input, right? It needs to know when it's at the very last word, because if it's at the last word in it, it needs to stop. It shouldn't go any further. Okay, so, it's also responsible for telling the outside world that it's done, that it's actually either found the key or has searched the entire Rolodex and not found it. And so our work, of course, is to build this state machine, which is going to take these 3 inputs and run through the Rolodex. Okay, and so after much extensive search and careful deliberation, we came up with this simple 3-state state machine. Okay, so we're going to sit in our chill state, S0, until we get a go. When we get that go, we're going to issue the high pulse. We're going to make first go high. Okay, now this, one of the reasons for using this edge detector here is it's going to generate a high for exactly 1 clock cycle. And so if we AND it with the state 0, we're going to get a nice clean pulse that we're going to be able to send out as first. Okay, once we land in state 1, basically state 1's purpose is to see if it should stop or keep going. So in state 1, if we're not at the last word and we still haven't found the key we're looking for, then we go to state 2, and in state 2 we issue a next. So next only depends on state 2. So again, we're going to get a nice clean pulse on next, because it only depends on being on state 2. Okay, and so we're going to bounce back and forth until either we're at the last word or we found it, or both. Yes? I could, because there's only one edge, I could have put it here. Yeah, so that's the thing, is you could have a Moore machine where you've written all the outputs on the edges, but it's still a Moore machine, right? The idea, of course, is that all of the edges leaving a particular state have the same outputs, right? So those outputs really don't depend on any inputs. Okay, it's good to write it in the state because then it's really clear that they're all the same.
I was thinking they just remove the state and they needed to not last, not found, then dash, then next and then loop to F1.
No, I don't want to do that because first and next have to be exceedingly clean.
Oh, okay.
And particular comparator can have glitches. Okay? These are asynchronous signals. Any kind of instability might be understood as part of the signal. Right? The beauty of our synchronous systems is our signals can do whatever they want when they're far away from the clock edge. It won't have an effect. But here, that's no longer the case. Okay, this is what makes our design simple in synchronous. We don't have to worry about things like that. Okay, all right. So everybody understand how this is supposed to work? Anybody not want me to go to the next slide? Okay, all right, let's go. All right, so we simulated this thing with our functional simulation. And in this particular scenario, we matched the key that happened to be word 3. Okay, and so when we got to word 3, we were back in state 0, and the ready flag went up, and the found was high. Notice that found is kind of, it can be anything if the data is unstable, and the data is not guaranteed to be anything specific between when the next is high, so we don't know exactly when it's going to change here. So that's why we put it as unknown. Okay, worked fine. Okay, so and this particular simulation is of finding the very first word. So this is where the key matched word 0. So we immediately found it. So we went from S0 to S1, which put the Rolodex at word 0, and we were in S1, and we say, aha, we found it. So we went right back to S0. We didn't even issue any next pulses. We didn't want to issue a next pulse. We wanted to be at word 0. Okay. All right. And here's our XSIM functional simulation. Okay. And you can see it working here. Our key was 0B, and we matched, which one did we match? Oh, I guess we matched this one, 81. And let's see. And here, I guess we didn't find it, and so we did another one. Okay. All right. Yes.
Why don't we mask found with 0 every time the data is unknown?
Why don't we what?
Why don't we mask found with 0 every time the data is unknown? Since what if found pulses, because it's unknown, right? What if it pulses a 1 in there, and that sets off some of the logic we have connected to the end?
Well, so by our protocol, you should not check found unless ready goes high,
I see.
right?
Ready only goes high.
Right? The way this works is you don't want to check found until ready's high.
Yeah.
Okay. All right. So far so good. Unfortunately, we then did a place and route and a timing simulation. And whoops, we have a problem. So when we did the timing simulation, it turned out that we had a little pulse on found here that went high. And when we were searching for word 0, we went right past it for some reason. So when we're searching for word 0, we should have gone from S0 to S1 back to S0, but instead we went to S2. And so we went right past word 0, even though that's the data we were searching for it. Okay, and part of the problem is we have this pulse on next here. How did that happen? That's not good, right? We weren't supposed to have a next until we got to state 2. This shouldn't be happening. Let's see. We're here. Next should only be high in state 2. When we did the functional simulation, we never got a next pulse. But in the timing simulation, we get this very short next pulse here.
Can I look at the diagram
Which one?
slide again?
No,
Yeah, that one with the state machine. I think I have an idea of what the issue might be.
you do. Okay.
Is it perhaps that not last and not found? Ooh, because I've
No, next should only be high when you're in S2. Next doesn't
Yeah.
depend on these guys.
I'm trying to think if there was a way the edge of not last and not found got triggered from state 0 anyway. Perhaps through information.
But
that
the
wasn't
problem is
set.
next. The problem is that pulse on next. Yeah.
Is it not synchronized? So you need to put a flip-flop between first and next?
So these are could be. We have a glitch on our logic. Are you suggesting that perhaps we want to do this? Yes.
The fact that you have it prepared in your slide is really suspicious.
That probably means it's not the right thing to do, right?
Yeah, especially since it's written in a way that question mark. Solution?
Someday I'm going to have to put that and it'll be the right answer. Okay. All right. So this is something you might be tempted to do to clean up that pulse on next that we have no idea how that got there. It's not supposed to be there. Maybe it's an artifact of how the logic was built. Okay. And this would in fact eliminate the pulse. It certainly would. Unfortunately, it's going to do some other things that we don't like. This is what we get when we put those flip-flops in them. Okay, so this is the original go pulse, and this is the original first, and this is the next, which had that unfortunate hazard in there. And this is the delayed version of first. And because first is delayed, so is word 0. Okay. And so by the time we get to S1, now we don't know what word is or found is. It's unknown, and so we may go off into unknown land. And so, not only are we not going to find word, but there's no guarantee what's going to happen after this. Okay, so this isn't going to work, right? Part of the problem here is that you are delaying when the signals reach the Rolodex, and this is going to delay when you get the feedback from the Rolodex. So your synchronization, the synchronization of the first and next with the feedback is off because you have got this delay, extra delay going in one direction, right? It's like when you're on the phone and you're talking to someone and you don't get their answer before you've said the next thing. Okay, so there are two approaches to this. We could go back and fix our state machine and have it wait for the feedback. But another solution is to look at why that next output has a pulse on it that we don't want. So let's look at the circuitry that was used to implement this state machine. Turns out that the signal next, which is only high in state 2, is the OR of two sorry, is the and of two state bits. So whoever implemented the state machine used the following state encoding. And remember, next is only high in state 2. So next is essentially the and of the two state bits, Q1 and Q0.
We want propagation delay.
And so, unfortunately, there is a slight propagation delay due to this would be due to wiring, since both of those things come out of flip-flops. Or there could be some skew between when the clocks reach those two flip-flops. Either one of those two could cause this. And so for a brief amount of time, when we switched from S0 to S1, Q0 went high first, and they were both simultaneously high. And that's how we got a pulse on next, because in the transition from S0 to S1, there was just this brief moment where they were both state bits were high. Okay. So how can we fix this? We use a different state encoding. And this is one thing that you're going to want to do if you have asynchronous outputs, is make sure that they are not, that they come from individual flip-flops directly, that there's no logic on them at all. Okay, so we're going to re-encode our states. Okay, so instead of making, what did we do? Whoa, go back here. We had state 0 be 0, 1. Okay, so we're going to change that so that state 0 is now 0, 0. So when we go from state 0 to state 1, there will not be any moment where both of these flip-flops are 1. Okay, so now if we look at the logic for next, we'll notice that we want next to be high when we're in state 2, and Q0 is high only when we're in state 2, so I can make my logic look like this. And now I am absolutely convinced that there will be no erroneous pulse on next. It will only be high when I am in state 2. Yes?
Will using one-hot encoding for your states flip-flops just fix this issue?
No. Right? Even if I had used one-hot encoding, let's go back. If I had used one-hot encoding and
So you could have just taken, like, if it was, for example...
yeah, but if I wanted it to be high in two states, I would have an or, and then the transition between two states were those. Yeah, it still could be a problem. So that alone won't help you. Okay, so what do we want to do? I lost my slide now. Okay, that one. We want to make sure that we encode our states so that the outputs correspond exactly to 1 bit of the encoding. Okay, so this fixed this problem. Okay, all right, so in general, if you have, say you have 3 outputs for your device, and they are going out asynchronously. So I want output 1 to be high in these 4 states, and output 2 to be high in these 2, and output 3 to be high in the last 3 states. What I can do is I'm going to I'm going to try to use this encoding for my states. Now the problem, of course, is state 0 and 1 have the same outputs, and state 2 and 3 have the same outputs. So I need to add another bit here, 1 more state bit to differentiate. So now every state has a different state encoding. I've used 4 bits for 5 states. But now when I write the equations for the outputs, I can say output 1 is Q0, output 2 is Q1, and output 3 is Q2. Okay, and you can do that in general, and that's one thing you're going to want to do if you have asynchronous outputs, is you're going to want to make sure those outputs come straight out of flip-flops. And if you don't want to play with the synchronization of your whole device, you can just use that as your state encoding. Okay, you may have to extend your state encoding if there are many outputs that have the same, many states that have the same outputs. Okay, all right. So that's what you want to do. Now, there is a whole discipline in logic synthesis that deals with keeping state machines or keeping two devices synchronized. And one of the ways, okay, we talked about just inserting flip-flops here. And we could have done that, but to keep this synchronized, what we would have had to do is take the signals coming back, the last and the found signal, and introduce what we call a negative flip-flop. So a flip-flop delays the signal by 1 clock cycle. A negative flip-flop predicts them. It tells you what your output's going to be from the next input. Okay, unfortunately, there's no real way to implement such a device. Okay, they're called they're also referred to as anti-latches or inverse flip-flops. But as part of logic synthesis, to balance timing, these are inserted. And if you insert 2 of them, your timing is still the same. And then you can move them around your circuit. You can slide them forward or backwards across logic. And the idea is you want to slide all of the inverse delays to the end, to the final outputs. And that gives you how much extra delay you've inserted by this. The whole process is called retiming of circuits. And so you may hear that term, but that is the actual process for dealing with this in an automatic way, in a mechanical way. Okay. There won't be any questions about retiming. Okay. Let's see. I still have a lot of time. So I can talk about interfacing to memories, or we can talk about Lab 6. Sure.
Yay!
Marco.
What was the first interfacing what?
So, because I wasn't sure you guys would have questions about Lab 6, I kind of felt you might, but I was thinking we could talk about, where did I put it though? I have to find them.
More importantly, is it going to be on a midterm? If it is, then we should talk about it. If not, talk about Lab 6.
Now that's not a good attitude. But so interfacing to SRAM is not part of this class, but it's maybe something you might want to do in the future, but not in this class. And it fits nicely with what we just talked about. But anyway, all right, so let's talk about Lab 6. Yes?
So I wanted to get clarification about edge case first.
Edge
So
case.
I don't
Okay.
think I saw this in the video, but I do understand that you can only hover when you're in the center track, correct?
Right. That is
Now,
close.
let's say that you're hovering and you press either the left or the right button at the same time.
Nothing happens.
I was gonna ask if that health bar should regenerate even if you're transitioning.
So the health bar is only affected by hovering, right?
Yep.
So but if you're hovering, pressing left and right should have no effect. So so really the hovering only depends on, the health bar only depends on hovering.
I see, because last night I was just thinking about like pressing the button, right, and then pressing the left button, right, and the health bar would be like stuck until I
No, it shouldn't.
see. Okay.
So So I mean, you have this. One way to think about this is the slug is either, if the slug is moving between tracks, or the slug is on the left or right track, you can't hover. And you can only hover when you're on the middle track. And once you're hovering, then if you're hovering, the health bar is going down, and if you're not hovering, the health bar is going up. Right? So you probably, one way to do this is to have it change state when slug change state when you're hovering.
Yeah. Well, I kind of relied on just the output of.
See, this makes things complicated. States makes things much simpler. Adding a state makes it a whole lot simpler and less prone to introducing a combinational loop.
I haven't had any combination loops
So
so far.
far. Yeah. Marco.
This is plastic. You need to go to that table.
That's plastic.
Oh,
This is weird.
Monopoly on
Yes.
My kind of method I'm thinking of doing is, obviously I have the energy bar, right? And then I would check when it's the minimum, and when it's the minimum, when it's not at the minimum, if and the button pressed, I enter the hover state and stay in the hover state. And then when the button is pressed, and then even though it's minimum now, that means the hover doesn't exist, and it goes back to no.
Right. You fall out of hovering if you have no energy. Of course, immediately you'll have a piece of energy and be able to go back up if you hold the button now. But then you'll go back down.
That's why the minimum, so that if it's already at the minimum, and it's going to constantly keep staying at the minimum until I release the button, and then it just start increasing, and then decrease gradually.
Oh, you're going to have to release the button. Oh, okay. That's not necessary, but it's okay. Any other questions, really? Yes.
Okay, so I already finished the health bar and the slug, and now they can interact with each other now. Now I am just confused on how we would get started on the trains. Like I understand like the initial positioning and all, but what I was just like really scratching my head about was the delay. Like I know that it's the left track that starts and the right, and it's the middle.
Okay.
I'm just confused on that. Like would we use like a flag to show like when?
So you're going to have a master state machine at the very top, right? No? And it could, tell the tracks when to start. In fact, you don't want anybody to start until you hit button C, is it? Yeah, I think, yeah, right? And so that can tell each track when to open, right? I think I used the word open. And then the top also can keep track of whether the slug crashed into anything.
Oh, because I was thinking that that crash signal, right, would just be in the slug, but I didn't think that the top module would be like the one that dictates it.
Yes.
Well, I was thinking for the crash signal, just check if, each module has a Drami signal, right? If the Drami signals are high for slug and track at the same time, then we
Have a crash. It just you must detect it right away. You must change state right away because that signal is only high maybe for 40 nanoseconds. Right? It's only at 1 pixel. You can't just check it every frame. You just Okay, I think there was a project one year where we had to check whether there was no crash. And for that, we had to go through an entire frame without having 2 pixels overlap, 2 things overlap. Yeah.
I was confused about how to make the trains like randomized.
Okay. So that turns out getting the trains to kind of behave in a way that makes the game interesting was actually a bit more complicated than I had anticipated. but the idea is there are 3 tracks, and basically each track is the same module except for where it is on the screen and when it gets the start signal or to open, right? And so you can make you can make a single module for a track, and then the top level just tell it each one when to open. Okay. Now within each track there are actually 2 trains, because otherwise you'd only see one at a time, right? Okay. Each train operates independently, but of course you don't want them crashing into each other. So what happens is that so you're going to have to make a module for a track, and within the track, there's something that controls both trains. Okay, so it's going to start one train, and then the train basically just travels down repeatedly until it's told to start again. Okay, so the track is in charge of telling the train when to start again. And when a train starts, it's going to pick a number from the LFSR, wait that amount of time, it's also going to pick a number from the LFSR for its length, so that they're not all the same size, which also makes the game more interesting.
So how do we know when to stop the LFSR? Because it's kind of like a roulette wheel, right?
Well, so what you want to do here is you want to let the LFSR just run. Okay, what you want to do is sample it and grab a value and load it into a register at fixed times. So for like the length, if you were just taking, what did we say the length would be? We said
Between 60 and 123, off the top of my head, the length of a train. It's B plus somewhere between 0 and 63, but B is always 60,
so the length of the train is 60 plus B. And B is fortunately a number that is between a power of 2, right? So 0 to 63. So you can just use you'll just need 6 bits from the LFSR. So what you want to do is you want to add 60 to a saved value, a 6-bit value, right? If you were to just use 6-bit from your LFSR and it was running, you would see a very wobbly train. It would have a solid part, and then you'd have kind of like a shimmering tail. Might be kind of fun, but okay. All right, so that's what you want to do. You want to sample the LFSR and hold values for it. Okay. The wait time, again, to do a random amount of time, you sample the LSR, load it into a counter, count down to 0. Okay, that's how you wait a random amount of time. So each train will have a counter for waiting, and then it'll have a register for its length, and those two will be initialized from the LFSR when it's told to start. Okay, so to keep the trains going one by one without running into each other, the first one starts, and then when it reaches a certain point, when its bottom edge reaches 400, it'll send a signal back to the tracks, telling the track to start the other one. And so they'll all just keep starting. Now, the first train, you can just let it keep going. It'll go off the screen, go way high, use very large coordinates for it. Use your 15-bit coordinate, and it won't come back. If you were to run a rectangle from the top to the bottom with using a counter with 15 bits, eventually that counter will roll over to 0, but not for 10 minutes. Okay, if you waited long enough, it would come back. But If you use the fewest amount of bits, if you only use 10 bits, then you'll see it come back. So don't do that. Use the whole lot of bits so that, okay. And so that first train can keep running, and when the second train hits 400, it's going to tell the track, okay, next, start the next train. And so that first train gets reset, and it starts again. And so that they kind of work in lockstep, but the gaps between them look like they're random because they're waiting a random amount of time, and their length is randomized a little bit. Okay, but there's a sufficient gap between them so that the game is kind of playable. We had to add the hover because it was impossible to make sure that you could always win by switching tracks. Yes?
Oh, I think you mentioned this like a few days ago, but I just kind of forgot about it. Like, how would you determine that the slug has hit a train?
Well, that's a collision, right?
Yeah,
That's you have a signal to draw the train.
Okay.
You have a signal to draw the slug. If they ever overlap by a pixel, right? You and those two signals. If you and those two signals, that and will be high only if they overlap at a particular pixel. Right? So you take that and of those two signals, and that's your collision detection.
Okay.
Yeah.
Will anding the sort of output to the LEDs allow you to also have the collision work on irregularly shaped sprites, such as if you bitmask out? Gotcha.
Right, but you can't make a 1 pixel slug. That makes it too simple, right? So there are restrictions on the slug. It's either going to be a 16 by 16 rectangles, or whatever mask you put on it has to actually touch all 4 sides.
Interesting.
Otherwise, you could just make the slug 1 pixel. Could still lose, though.
Could a good faith sprite art work
Yes,
that doesn't quite touch all 4 sides?
sure.
All right.
Okay, but please don't do that until you get it working.
Yeah, of course.
Yes.
For the LSFRs, for the time, the random time, and the random length, did you just use a conditional to check like the back side is equal to like the 400 sound? As the reset for the random numbers?
Well, you don't really need to reset it. You can let it run. Why would you want to reset it?
Or to generate a new number?
I would just let the LFSR run. It's when you sample it that matters, right? For lab 5, you probably just ran it when you were in the idle state, right? Well, you didn't have to, but that was an easy thing to do because you weren't showing it then. But for in this case, you're going to want an LFSR just to run because you want to sample it at various times, and you want it to be random, so you want it to run, right? One thing to know is that if you have multiple LFSRs, they're all going to be identical, right? If they all start at the same value, they're all going to run. So there's really no point in doing that. You might as well just have one of them. What you can do is, what's happening here is they're getting sampled at different times, right? When you push button C, we don't know where the LFSR is when you push button C to start the thing. And then because the tracks are opened at different times, those trains will be sampling the LFSR at different times. And they will be hitting the 400 and starting the next train again, which will wait. So it isn't actually random. The only random part will be when you hit button C. But you'll get a different game every time you start it with button C. The other thing you can do is if we were starting all the trains at the same time, what we could do is use different bits. Right? The LFSR gives you 8 bits, but you could actually use just 6 bits. And you could use a different 6 bits for each track, so that they wouldn't all be the same. There's a lot of ways to go here. Any other questions? How much time do I have left? You want to? Yes.
Oh, sorry, I just need a bit more clarification on that master state machine on the top module. So I'm assuming it's just extremely short because
Yes.
it's just communicating when to start the game, when to the train should come down, right? And just when it communicates to both the train state machine and the slug state machine when like a crash has occurred. I see. Okay, so it's like really, really small.
Yes, it's not complicated at all. But
Okay.
it makes your design a whole lot simpler than having these things talk to each other. And
So does that
it's easier if you have somebody directing traffic.
right? But so does that, or this is kind of like my workflow, right? So since I finished the health bar and the slug, should I then do the state machine for the train and then do the master state machine?
You can do it that way because you can just ignore the collision issue.
Right, because I just like was scrambling my brain, like I had to rewrite this, rewrite that.
No, the trains are oblivious to the slug, right? They don't care.
Right.
And the slug, again, the slug just needs to know when to start and then when to stop. And while you're working on the train, you can have the slug there and have it move and
Okay, so not much.
do the collision last. Or one of the things you're asked to do here, or suggested, is to actually it's one of the requirements. I thought I put that in there. There's a cheat switch where switch 3 where the slug is immortal and you can't. So essentially you're doing that first by default. You're not, if you don't implement the collision, it's like switch 3 is on.
Right.
But the idea of a switch 3 is that you can watch the tracks and see what happens without actually worrying about not dying. Okay. So yeah, don't worry. I would worry about collision last. Any other questions? No. Okay. Want to hear about SRAMs? No. No? All right, another time. Okay, I'll see you. Wait. On Wednesday is dedicated to review. If you don't bring any questions, I will talk about SRAMs.
Okay.
Why are you phrasing it like that's a threat?
I'm
Threatening us is a good time.
I'm just kidding.